It's my pleasure to be hosting Kieran. Kieran Pastor is a fifth-year PhD student at University of Toronto, supervised by Jimmy Ba and Shelia McGilwraith. Kieran research lies in the intersection of sequence modeling and decision-making. His work has formalized how sequence models can be made to make optimal sequence decisions, even in stochastic environments through specially optimized prompts. Kieran also works on LLM reasoning and data efficiency, and also has work on data efficiency for frontier models within Google Research. In this talk, he's going to talk about OpenWebMath, an open dataset containing 15 billion tokens of mathematical web text from Common Crawl. OpenWebMath has been used to recently train Lemma, an open language model for mathematics. Kieran, feel free to take it away.
Yeah, thanks so much. I'm really excited to be here, and really excited to present our work called OpenWebMath, which is this massive data set containing basically the majority of mathematical text on the internet. And this is done in collaboration with Marco, who's here, and Jean-Pierre, and one of my two supervisors, Jimmy Ba. And so first, I just want to say, something that motivates me, and something I think that motivates a lot of researchers these days working on language models, is that we want AI that can reason. And so this is going beyond just sort of these language models that maybe are memorizing the solutions to something, but actually language models that can maybe see a new problem that they've never seen before and derive some sort of solution step by step. And so one example of this that we've seen recently is this language model GPT-4, which I'm sure everyone knows about. And so when OpenAI released GPT-4, they tested it on this wide array of high school level exams. So this includes things like the AP exams, SAT, GRE, and some math competition, etc. And sort of by scaling up their language model to GPT-4, they're able to pass the vast majority of these exams. And so this is actually how we evaluate our students. So I think any sufficiently strong language model that's able to reason should probably be able to do these. And so we have an existence proof that something like this can exist, but we actually know basically nothing about how GPT-4 was trained. And so on the other side, last year, a team at Google published this model, which they call Minerva. And so similar to GPT-4, this model is really strong at these quantitative reasoning problems. So they evaluated it on a bunch of undergraduate or high school level, math, physics, bio, etc. questions, and this model performs extremely well. And unlike GPT-4, there's actually a lot of details published about how Minerva was trained, and basically the recipe that was used to train Minerva. And so at a high level, Minerva is trained by fine-tuning Google's back then flagship language model called PaLM on billions and billions of technical tokens from scientific papers from arXiv, as well as this data set of mathematical web pages. And so this shows the data composition that Minerva was trained on. And so just like PaLM was, Minerva is trained on this general natural language data, but only about 5% of the data is trained on is this. The other 95% comes from scientific papers and from this data set of mathematical web pages. And so for natural language data, within the academic and open source community, there's actually a lot of work that has gone into sort of making data sets like this. And for arXiv papers, there's also some great data sets out there which take the contents of arXiv and process it to be suitable for pre-training language models. But we don't have really an equivalent for this math web pages data. And so going back to this original motivation of creating these AI reasoners, I think no matter how you envision us getting there, I think a good, reasonable thing to do would be to collect as much high quality reasoning data as we can. And so this is where this project comes in. And so we basically do this with OpenWebMath. And so OpenWebMath, our main objectives with this project were to reproduce this math web pages data set from the Minerva paper to the point where we can train our own open source Minerva. And second, we want to go a bit further than Google did in their project by not only creating this, but documenting it like more thoroughly and open sourcing the whole pipeline for extracting these mathematical documents from the web. And finally, just like a high level goal would be that we want to optimize for high recall throughout this whole pipeline. So we don't just want to find like the most high quality math documents from the web, but we want to sort of find like every document that we can from the web to train these models with. And so what I'm going to do during this talk is give sort of a walkthrough of exactly how this pipeline works and sort of the problems we ran into and the engineering solutions that we came up with, and yeah, just document this. And so I think natural place to start from would be Common Crawl. And so Common Crawl is this like openly available web crawl where every 2 to 3 months for the last 16 years, they crawl this massive portion of the web. And each crawl that they release contains about 100,000 of these compressed files that contain each like tens of thousands of HTML pages. And so in total, Common Crawl gives us around 200 billion HTML pages crawled from the last 16 years of the internet. And so I guess some of the technical problems here are that if you want to do anything with Common Crawl, it requires this enormous amount of CPU hours to process. Secondly, it's overwhelmingly the documents in Common Crawl are duplicate. And also, of those documents that are unique, only a small fraction of those have high quality coherent text. So like many of the documents in Common Crawl actually are just like sort of junk. And finally, of those high quality documents that you might even like think about ever training a language model on, only some small fraction of those are related to math. And so the goal here is to take this Common Crawl data set and distill it down to all the pages that are high quality, unique, and related to math with OpenWebMath. And so at a high level, we start with these 237 billion HTML pages in Common Crawl, and we have a bunch of stages to our processing to end up with our data set, which contains like 15 billion tokens and around 6 million documents. And so this includes stages like pre-filtering, language identification, these different quality filters, which I'll describe in more detail, this de-duplication stage, and then some manual filtering to get to this final data set. And so in this talk, I'll go through each of these in more detail and why we created them and how we arrived at this pipeline. So starting with pre-filtering, you'll notice that the pre-filter goes from this over 200 billion pages down to 1 billion pages in Common Crawl. And I guess the high-level idea here is that any code that's run on the 200 billion documents needs to be super fast. And we want to get rid of everything that's like very obviously not a high-quality document or not like a math page. And so what we do here is we have these very fast filters. For instance, we look for terms in the HTML text, for instance, like math jacks or these math tags or common common things like ktex or like the word text or something. And anytime that one of those appears, we pass it through the pre-filter. We also use this list of the top 100 LaTeX commands. And so if one of those shows up in the text, we also will let it through. And otherwise, we run this really fast math classifier. And so basically, this is just like a very, very high level, very fast filter to say, like, these are the things that are likely to have math, and we should take a closer look at this, and everything else we'll just throw away. And some notes here are that basically this is the step that required a ton of tuning to get a good balance of recall and speed. And so there's basically decisions here where you could maybe get 10% more documents, but then it would cost 3 times as much to process the data set or something. So you need a really good trade-off here. And like basically the exact code that you write here actually really matters because you run it so many times. For instance, by optimizing the regular expressions, we get a massive payoff for doing the exact same thing. And yeah, so that's the pre-filtering stage. Basically run over 200 billion documents, and we end up with 1 billion documents. Yeah, so I think, so the question that I see is, how do we come up with this list? It seems like it's basically about technical formatting rather than content. Yeah, so I think it's very hard to do any filtering based on content without spending a lot of compute. And so here we just pass things that have like vaguely math-related things, any sort of LaTeX symbols or terms that are related to math. And we don't take too close a look at the content just because it's too expensive. But later on, I'll talk about how we can filter based on the content as well. Okay, so now we move on to the text extraction. And so this is where we turn these HTML pages into this formatted markdown. And so at a high level, we want to convert all of these documents into markdown syntax, which includes formatting tables, headers, and lists properly. We also want to preserve equations in their original LaTeX code. And so this is really important because I'd say like the majority of these text extraction libraries out there, they do a good job at destroying all the math on the internet, right? So you know, like either the equations disappear completely, or you lose out on like some of the operations or some of the formatting to the point where it doesn't really mean anything anymore. And finally, we want to remove boilerplate. So that's like all the ads, sidebars, menus, buttons, etc. And so for the LaTeX extraction, actually the Minerva paper detailed their LaTeX extraction in their appendix. They mentioned that the majority of the documents come with math in the format of these script tags with type equals math/LaTeX. And the rest of the LaTeX appears in these annotation tags. And so we first went through, processed a lot of Common Crawl, and we looked at the types of math that we were finding. And it turns out this is not found in Common Crawl at all. So that was a major problem. And so this is like the beginning of the journey of figuring out how LaTeX actually appears in Common Crawl. And so it turns out that these script tags actually come from this library called MathJax. And when you look at how MathJax appears in Common Crawl, you get these 3 components. You get somewhere in the page, you'll have this script tag, which contains this configuration for MathJax. And so this will contain the delimiters that the page wants to use to represent LaTeX. And then somewhere else, you'll actually import the script for MathJax. And then within the text of the page, you'll just write the delimiters and write your LaTeX inside. And so what we quickly realized is that in Minerva, these scripts were already run before they did their processing. but in Common Crawl, they didn't run the scripts. And there's a bunch of technical problems too, where sometimes they might not import mathjacks from this URL. It might be buried within some other arbitrary URL, or like in some other file they import it. Sometimes they don't have this configuration, etc. So it's actually a bit of a challenge to figure out, when do documents actually have LaTeX in them? When are delimiters actually supposed to represent mathjack delimiters? And so the challenge for us was, okay, let's go back and figure out all the different ways LaTeX could be formatted in Common Crawl and make sure we support everything. And so what we did is, to sort of figure out like what are all the different ways it could appear, is we gathered like over 100,000 HTML files from Common Crawl, and we filtered it down to documents with this \frac in it. And so the reasoning here is that this is like the most common LaTeX command that appears in math. Like you can imagine all sorts of fields, all sorts of different types of documents would have at least some sort of fraction in it. And basically, like every time this appears, it is math somehow. And then iteratively refine the code until every time frac appears, our code is able to extract that into LaTeX code. And so this basically revealed to us many, many different formats that LaTeX can appear in Common Crawl. So one of them, which Minerva actually didn't get, is the fact that sometimes there's web pages which have images on them, and then these images in their URL or in their alt text will have LaTeX. So for instance, there's sort of web pages out there where like you pass the LaTeX into the parameters in the URL, and it'll return an image of that LaTeX equation. And so I think that's like including like Terry Tao's blog or something. So getting that right is pretty important. You also have this delimited math, which I just mentioned. And then finally, you have these types of math that were reported in the Minerva paper, where it's like inside of these math tags or something. And so what we found is that like most of the math on the internet is actually these mathjack tags, but a lot of it is sort of like these tail cases where there's these like different types of math. And so it's important to go through and just refine the pipeline until everything works. And so that's what we did for LaTeX, and we make sure that all the LaTeX on Common Crawl that we could find is sort of being extracted properly. And then for the rest of the text extraction, you have to deal with boilerplate removal. And so here's like an example of math overflow. And you can see like we want to extract like the title of the article, we want to extract the contents, maybe even some of the comments down there, and the answers, maybe the amount of votes it has. But there's other things that we probably don't want to be showing up in our markdown files. For instance, buttons to sign in or search, these calls to actions that appear like on every page. There's these navigation bars, or even like related posts. So stuff like that we want to get rid of. And so we considered several open source text extraction libraries in Python to do this. And the most important point here is that we really don't want to remove any sort of math when we're removing boilerplate. And we found that these libraries basically have a tendency to not work that well, or just like remove math or remove very important things on the websites that we care about the most. And since we're making this math data set, there's actually not too many pages that contain like all the important math on the internet. And so making sure that we have the ability to customize this extraction to make sure it works on those pages is really important. And finally, we also note that we tried a bunch of these libraries and found that like really they're not all that great, and some of them are very slow. So the one we settled on is this parse library, which you see like got through 1,000 web pages in 4 seconds, but some of them take like 300 seconds. Some of them, like just text, which was used to make the pile, are like 10 times slower So we decided to build our own boilerplate removal on top of Mozilla parse. And our key design choices here were, one, we lean heavily on CSS selectors to remove boilerplate. And so we sort of go through our pages iteratively and add common CSS selectors that we think like usually correspond to boilerplate. Two is that we iteratively refine the text extraction to make sure it works on the common domains that we have really, really well. And then three, since we're developing all of this sort of vertically, then we can use the math extraction annotations that we gathered before to avoid removing any components that have math. And so at a high level, our text extraction pipeline looks as follows. We have LaTeX extraction, where we go through like around a dozen different types of ways LaTeX can appear and extract the equations into plain text, into LaTeX and tag them. We have this DOM processing to tag headers, tables, and remove sort of like linked clusters. And then we use the extract plain text method from Mozilla parse to extract the plain text with this list of blacklisted CSS selectors. And finally, we have like this post-processing, which removes all these like empty header sections, common boilerplate text, and footers, and escape all the non-LaTeX $ in the document. So this is like a whole text extraction pipeline, and yeah, there's definitely more to talk about here, but let's move on to filtering. So I guess now we have 1 billion. We have 1 billion documents in the HTML in the Markdown format, but not all of these documents are high quality, and not all of them are related to math. And so the filtering is like aiming to solve this problem. And the first thing that we do here is this language identification filter. And so like the reason for having a filter for language here is since our pipeline is tuned for English text, and English is, like basically I wouldn't be able to tell if it was working well in other languages. So that's why we primarily focus on English for this data set. And so we just remove all the non-English documents. One detail is like we normalize all the text and remove the equations before we pass it into this classifier. And we just use this very commonly used fast text language identification classifier to get rid of the non-English documents. And so this brings us down to around 336 million documents. The second filter is we want to filter for math content. And so we tried many approaches for scoring how mathematical a document is automatically. And so the first approach we tried is gather a human label data set. And so this was me sitting down one day for the whole day, just scrolling through documents and labeling them as math or not math. And I got through maybe 1,000 of these. And I would say the accuracy is pretty high, but the quantity is very low. And when we train a classifier on this, it's not too great. The second approach we tried is gathering a GPT label data set. And so for this, we can gather not 1,000 or 2,000, but we can gather maybe like 20 or like tens of thousands of examples pretty easily. But I'd say like from inspecting it, the accuracy is actually pretty poor here. One problem is that the documents are pretty long and you have to sort of pick like a snippet of the document to pass off to GPT, and GPT will judge whether there may be some math in the document, and it doesn't seem to really understand what that means. And we get much better results when we use GPT-4 than GPT 3.5 here, but obviously we don't want to spend too much money on that. And then finally, the last thing we tried is creating this self-supervised data set. And so I'll mention what this is in a second, but here we get pretty good accuracy, not as good as the human label ones, but we get an extremely high quantity, so maybe on the order of millions of examples. And so this this classifier and this self-supervised approach we call math score. And how this works is we have this text corpus that contains documents that may or may not have math. And what we do is we remove all the LaTeX equations that we detect in these documents, and we train a classifier to predict whether one of these top 100 LaTeX commands that I mentioned in one of the previous slides exists in this document. And so what this trains the classifier to do is based on the surrounding words, not based on any equations or anything, based on the surrounding words, does this document seem like a document that would have LaTeX in it? And so this learns to find words that correlate very strongly with the presence of these LaTeX commands. And so doing this, we can take like millions of documents, train this classifier on them, and it turns out this classifier is pretty good to the point where like there's a clear separation between the documents that have math in them and the documents that don't. And for our filtering, we use these different thresholds for this filter based on whether our extractor in the text extraction phase detected LaTeX. And so if the document has LaTeX that's detected, we keep all the documents that have over like a 17% chance of having math as judged by our math score classifier. And if there's no LaTeX in the document detected, most likely the document doesn't have math, but maybe there's some math that we didn't detect. Maybe the document just doesn't use LaTeX for some reason. And so here we'll keep documents that have over 80% chance of having math in them. And so this lets us keep documents that didn't have LaTeX or where our pipeline didn't properly detect the math. And finally, for our filtering phase, we have this perplexity filter. And so the previous step was just filtering based on whether something was math or not. Here, we just kind of want to do a final pass over the data and filter things that just don't look like English or don't look like high quality documents. And so mainly this is things that are like very repetitive or very corrupt in the data set. And so what we do here is we do something which is very common in these pipelines, which is we train this n-gram language model called KenLM on this previous math data set called ProofPile. So this is like a couple billion tokens of math data. And so we train this simple language model on that, which gives us the ability to measure the perplexity of documents in our data set under this model. And if any of the documents are just too shocking or too surprising to this language model, we just get rid of them. And so this is the sort of final filtering step for OpenWebMath. And now we end up with 59 million documents. And as I mentioned before, many of these are duplicate. And so for this, we use an approach that I think a lot of other people use, which is like, there's this GitHub library out there called text dedup. It implements this SymHash algorithm, which is this approximate deduplication that's pretty efficient. And we apply it to our data set with this threshold of 0.7, which means like things don't have to actually be exactly overlapping for them to be considered duplicates. And we find that there's like this massive duplication rate. And I'm not sure whether the duplication rate here, which is like you end up with like around 8 million documents down from 60 million, whether this is like specific to Common Crawl or if it's just something that's specific to Common Crawl after we filter for all this math stuff. Like maybe we end up finding very similar things. But yeah, so there's a massive duplicate rate, and we went through and inspected, and it seems like these documents really are duplicates. And I guess one thing from development that I thought is pretty interesting is that this massive duplicate rate, it sort of makes it hard to reliably predict how many unique math documents exist in Common Crawl. So like we started the project by extracting not all of Common Crawl, but only a small chunk of Common Crawl. And we found, okay, like we have gotten 5 million documents or something after processing a third of Common Crawl. So does that mean that we'll have 15 million documents at the end, or how many documents will we have? And really the actionable thing here is like, do we stop processing Common Crawl after extracting just a portion of it, or do we do the whole thing? And so to solve this, I think we came up with something that's pretty interesting, which is like we sort of try to make scaling laws here as well. And so we basically use curve fitting to predict the number of unique documents in Common Crawl after extracting the whole thing, just based on the first few shards of Common Crawl. And so what we do is we basically measure the percentage of duplicates that we find after deduplicating in Common Crawl. And we fit this curve, which is parameterized like this. And we find that like even based on the first few data points, we get a really good fit for how many duplicates there are going to be. And like even you can get rid of this point and just fit on like the first two or something. And it seems very powerful. And then of course, like once you have the percentage duplicates, you can transform this into like the total number of tokens and get like a pretty reliable fit here. And so I guess based on these curves, we decided that, okay, like it seems like even after extracting like 20 or so of these shards, that we should probably continue past 100 and just do everything, because we're still getting a lot of tokens. And so this is sort of our deduplication work. And then finally, like as you saw back here, we had around 50 billion tokens. So we thought that we initially had 54 billion tokens in OpenWebMath. And after some beta testing, we quickly realized that there's actually a problem, which is that the majority of these tokens were from these search result pages. So basically, like there's some pages online which are like, people would search for some math-related term, and then there'd be this massive page generated that has like just a list of different pages, and sometimes LaTeX would even appear in them. And this was like a mass, even though there's not that many documents, these documents were huge, like sometimes up to 50K tokens or something. And so when we realized this, we actually went through and did some more manual filtering on the data set. And so basically the trick here was like, just sort the domains by number of characters and go through maybe the top 1,000 and see what you find. And if there's something that is like very clearly not math web pages, we just got rid of it and added some manual filters. And so this only took us down about 1 million documents, but it took us down like many, many billions of tokens. But the nice thing was that like after we did this filtering, we found our downstream evaluations went like way up. So even though we got rid of a lot of data, it's actually much, much higher quality. And so that is all of our pipeline for OpenWebMath. And we did some quick inspection to see like what type of data appears in here. So here's like the top domains by character count. And we also basically made these little like GPT scripts to go through documents and classify them as like different subjects or different types of documents. You can see a lot of the data set is actually these forum posts. And so this would be people like maybe they ask a question about some sort of math problem and the people are helping them solve it. And you have like different references or like blog posts or something. And most of the documents are math, but there's also a lot of physics, computer science, other stuff. I guess our philosophy here was like, if it's technical, if it has LaTeX and it has like this problem solving sort of feel to it, then it's good. And so that's why like we let a lot of these like different STEM subjects appear as well. And so yeah, we end up with 6.3 million documents, 14.7 billion tokens. And the question now, and I think a very scary question, is how good is it? Like you do all these steps, you spend all this money to process this data set, and basically, like, how do you even tell whether you made these decisions correctly or how good the data set is? And so our basic approach here was to just train small language models from scratch on the same amount of tokens of different data sets, including OpenWebMath, to compare, like, on a per token basis whether OpenWebMath is like outperforming these other data sets or not. And so we took these 1.4 billion parameter Pythia models, and we trained them from scratch on the pile, on proof pile, and on OpenWebMath, and on a mixture of OpenWebMath and proof pile. And so for those who are not familiar, the pile is like this collection of a bunch of natural language sources. Proof pile is mostly arXiv documents, but also like one or two, like also like a small collection of like math, formal math, and math textbooks, and we're OpenWebMath. And so basically what we did is we ran both a perplexity evaluation and accuracy evaluation. And so for perplexity, it's basically saying, like, we do this few shot prompting, we give it a question, and then we look at the likelihood of the chain of thought answer that's provided in the data set. And so we look at these two benchmarks, DSM-AK and MATH, and we found that actually the model is trained on OpenWebMath and the model is trained on like a mixture of OpenWebMath and proof pile perform really, really well and have like a very low perplexity on these data sets. And surprisingly, they actually outperform this Pythia 1.4b model, which was trained on 300 billion tokens. So like order of magnitude more tokens of general text, we're actually outperforming that. And we also tried on like accuracy as well. So this is the easy algebra questions from this MATH benchmark. And you can see that these models trained on the pile or proof pile are not very good at solving these questions. But with the right type of prompting and decoding and right data mixture, you can get like 10% on this data set, which I think is pretty impressive for such a small model. And it's double what Pythia is getting. And so it seems like OpenWebMath is like very, very dense with good math knowledge. And if you were going to train a math model, OpenWebMath is probably the right choice of data set to use. And so, of course, going back to the original goal of this project is like, we want to reproduce not just this data set used to train Minerva, but also take a stab at like reproducing these Minerva models that can reason as well. And so I'll very briefly go over our adventure in scaling this up in this paper that we also released recently called Lemma. And so Lemma is a sister project to OpenWebMath, where we try to reproduce the Minerva model. And so what we do is we train not only on OpenWebMath, but on arXiv papers and this data set we call algebraic stack, which is a collection of all sorts of math code, including formal math taken from GitHub. And this sort of roughly matches what Minerva was trained on. Minerva is only trained on arXiv and webmath. We also train on like this code subset. And we evaluate it on all sorts of benchmarks, like the very common ones, MATH and DSM-AK. We evaluate on Python-assisted math. So math where like you don't just directly solve it with chain of thought, but you write a program to solve it. And also on these formal math evaluations. So for instance, taking informal math and formalizing it, and also this formal to formal theorem proving task. And so basically, when we trained this model, we found that it actually performs extremely well. And so this is the MATH performance of our model. And this is like sort of the scaling curve of Minerva. So they train like this 8 billion model, this 62 billion model, and somewhere over here is like their 540 billion model, not included on the plot. But basically what we find is like our lemma model gets roughly the same performance as, or like similar performance as the 62 billion model at only 34 billion parameters. And so there's some conflating factors here, confounding factors here. Like for instance, this is like initialized with a much worse model than lemma was. But I think, for a large part, we've been able to reproduce the Minerva results here. And so we show our informal math evaluations as well as like the informal to formal and formal to formal, and lemma performs really, really well across the board. And also recently did this evaluation where inspired sort of by the recent XAI release with their Grok model. What they did is like when they came out with Grok, they not only evaluated on these common benchmarks, but they also evaluated on this Hungarian math exam, which was released after the pre-training data was extracted and after the models were trained. And so the interesting thing here is like now it's actually impossible to memorize the solutions because the test like wasn't online when we trained the model. And so what I did is I went through a bunch of open source models and hand graded their exams on this Hungarian math exam and compared it against this known benchmark, GSM-8K, where people like may or may not have trained on the test set, or like I think more likely is that they just tune things until it works really well. And so what you find is like there's these two very distinct clusters here where there seems to be like a clear scaling curve of math capability, where like the exam score and the GSM-8K score are raising at the same rate. And you can see that lemma actually appears to compete quite well with GPT 3.5 Turbo, which is really cool. Like it's not just that it's getting like the same benchmark scores on GSM-8K, but when you give it like a completely held out exam, lemma 34B with zero post training actually is competing with GPT 3.5 Turbo. And then you can see like there's these other fine-tuned models that appear in this red cluster up here, which it seems like sort of like overfitting somehow to these benchmarks. So I think this just shows like lemma seems to be like generally good at math, no matter whether it's like a benchmark that people commonly evaluate on or just like some random new math problem or new math evaluation that comes out. And some other highlights from lemma, since we have the data set, we did a thorough contamination analysis. And basically what we concluded is that contamination doesn't really affect the benchmark scores here in a way we can measure. And so like what we found is that out of the 5,000 MATH problems, only around 300 of them show up in OpenWebMath. And if we measure the contamination, or we measure the performance on like this contaminated subset of the benchmark versus the sort of like not contaminated portion of the benchmark, the performance is roughly the same. Like there's not a big difference. And so I think like in general, it's actually a pretty interesting, I guess this seems pretty similar to how other papers did it. Like instead of decontaminating your pre-training or like training data sets, you decontaminate the benchmarks and you look at the performance difference between your contaminated and decontaminated versions. And so we provide like a pretty thorough analysis of this in the paper. We also find lemma performs significantly better at math tasks after fine-tuning the other models. So there's this recent fine-tuning data set called MetaMath that came out. And it turns out that like if you evaluate the 7 billion parameter lemma model on MATH, it gets 18% performance. And if you fine tune it for like relatively zero compute on this MetaMath dataset, it actually goes up to 30% performance. So there's a lot of like untapped power, I think, here in these lemma models. And we also made a pretty cool sample exploration tool. So this is our sample explorer. So you can try like all the different evaluations that we did on Lemma, like algebra, like these are all the MATH tasks. You also have GSMAK, OpenCourseWare, MMLU, and the SAT. And you can see like rendered in LaTeX the steps that the Lemma model takes to solve the problem. And I guess like finally, because our goal of this was to like open source and sort of take this reasoning progress that was brought about in Minerva and sort of like bring it into open source and like show everyone exactly how you can make this. We released the entire pipeline for OpenWebMath processing on GitHub. We released the Lemma training and evaluation code on GitHub. We have a Hugging Face for OpenWebMath, the Lemma models, and also these like math score and perplexity models. And we've finally also released like 2 papers. So there's the OpenWebMath paper, which contains a ton of information about all the steps to make OpenWebMath, and also the Lemma paper, which includes like how we trained it and all the evaluations and all this analysis and stuff. And so yeah, so this wraps up my talk. And thanks everyone.
That was awesome. Do folks have questions? Feel free to unmute yourself if you want to ask any question. I have one that touches on where you were talking at the end around like potential of like the fact that by fine-tuning on a specific task, you get a nice bump in performance. I have a sense of, on web trained model, why that, general web text, why that might work is just you adapt instead of like doing continuation. You adapt to the format of the task, and that's why you get one of the major reasons why you get improvement. Do you think it's the same for math model? Is there anything else there that it's special about solving math problems?
Yeah, well, I think like from looking at the sample exploration tool, what I noticed is that like sometimes I think the very common mistakes that the model makes is sort of like either skipping some steps, or I think it's just the types of chain of thoughts that are induced from our few shot prompt are often not that optimal. And so I think just improving the way that the model is like few shot is doing its chain of thought and reasoning will probably make a big improvement in how in the performance here. So yeah, that's probably why. But I'm actually not sure whether like this MetaMath dataset contains like a much better chain of thought than we have in our few shot prompt. I guess one thing is like for this dataset, right? Like it's basically a GPT-4 distillation, and so GPT-4 had this whole like RL process where it tries to like go through and I guess sort of like search for these best ways to answer the questions such that it's actually accurate. And so maybe by distilling that down into our model, we like can share some of the benefits of this search, where maybe language models are able to do some things in one step and some things need to be written out in multiple steps. And we have some intuition about that, but GPT-4 like maybe found like this optimal trade-off, and distilling that down into our model is like a really important.
Interesting. I guess another question, like this is still about Lemma, is how do you think about mixtures of pre-training data for a math model? Did you experiment with mixing some general domain text as well? Did you try adding code or anything that I wonder if there's anything different in the recipe you have to follow there.
Yeah, so I think mixture is really important. So what we did here, which I think is not too optimal, is we trained for, I think, only around, like on the order of 10 billion tokens, a couple models with different mixture rates. And so we vary like how we mix the web data, the code data, and the arXiv data, basically. And we fixed like the general domain data to like 5%. And we just picked the mixture that works the best there. Of course, like there's some problems here, which is that like I think when you're talking about mixtures and stuff, you have to consider repetition also. And here we only have like 15 billion web tokens, and yet our data mixture was actually like 4 to 1 to 1, whereas like web to code to papers. And so our data set got repeated like 8 times basically during this continued pre-training. And so yeah, I think like you have to consider all of this when you're picking your data mixture. I think like one thing that we noticed is that actually like the code is probably too small, given that like a lot of what you want to do with this model is sort of like formal math or code assisted math, and yet it seems like we have very little code in our training, right? So
Cool. Thank you, Marco, for the pointer. Any other questions from folks on the line? If not, let's thank our speaker one more time. And I think you have a bunch of one-on-ones scheduled. But yeah, thank you so much for the talk.
Thanks.